At the end of this video, you should be able to distinguish between inversely and directly proportional relationships. Chapter 2, Section 3, Using Sample Problems. Learning to analyze and solve such problems requires practice and a logical approach. In this section, you will review a process that can help you analyze problems effectively. Most sample problems in this course are organized by 4 basic steps to guide your thinking and how to work out the solution to the problem. Analyze. The first step in solving a quantitative word problem is to read the problem carefully, at least twice, and to analyze the information in it. Note any important descriptive terms that clarify or add meaning to the problem. Identify and list the data given in the problem. Also, identify the unknown, meaning the quantity that you are being asked to find. Then plan. The second step is to develop a plan for solving the problem. The plan should show how the information given is to be used to find the unknown. In the process, reread the problem to make sure you have gathered all the necessary information. It is often helpful to draw a picture that represents the problem. For example, if you were asked to determine the volume of a crystal given its dimensions, you could draw a representation of the crystal and label the dimensions. This drawing would help you visualize the problem. Decide which conversion factors, mathematical formulas, or chemical principles you will need to solve the problem. Your plan might suggest a single calculation or a series of them involving different conversion factors. Once you understand how you need to proceed, you may wish to sketch out the route you will take, using arrows to point the way from one stage of the solution to the next. Sometimes you will need data that are not actually part of the problem statement. For instance, you'll often need to use data from the periodic table. Compute. The third step involves substituting the data and necessary conversion factors into the plan you have developed. At this stage, you calculate the answer, cancel units, and round the result to the correct number of significant figures. It is very important to have a plan worked out in step 2 before you start using the calculator. All too often, students start multiplying or dividing values given in the problem before they really understand what they need to do to get the answer. Evaluate. Examine your answer to determine whether it is reasonable. Use the following methods when appropriate to carry out the evaluation. 1. Check to see that the units are correct. If they are not, look over the setup. Are the conversion factors correct? 2. Make an estimate of the expected answer. Use simpler, rounded numbers to do so. Compare the estimate with your actual result. The two should be similar. 3. Check the order of magnitude in your answer. Does it seem reasonable compared with the values given in the problem? If you calculated the density of vegetable oil and got a value of 54.9 grams per milliliter, you would know something is wrong. Oil floats on water. Therefore, its density is less than water. So, the value obtained should be less than 1.0 grams per milliliter. 4. Be sure that the answer given for any problem is expressed using the correct number of significant figures. Look over the following quantitative sample problem. Notice how the 4-step approach is used in each, and then apply the approach yourself in solving the practice problems that follow. Calculate the volume of a sample of aluminum that has a mass of 3.057 kilograms. The density of aluminum is 2.70 grams per cubic centimeter. Analyze. Given, mass is equal to 3.057 kilograms. Density is equal to 2.70 grams per cubic centimeter. Unknown. Volume of aluminum. Plan. The density unit in the problem is grams per cubic centimeter, and the mass given in the problem is expressed in kilograms. Therefore, in addition to using the density equation, you will need to use a conversion factor representing the relationship between grams and kilograms. 1,000 grams is equal to 1 kilogram. Also, rearrange the density equation to solve for volume. Compute. The answer should be rounded to 3 significant figures. Evaluate. The unit for volume, cubic centimeters, is correct. An order of magnitude estimate would put the answer at over 1,000 cubic centimeters. Because 3 divided by 2 multiplied by 1,000. The correct number of significant figures is 3, to match the number of significant figures in 2.70 grams per cubic centimeter. Direct proportions. Two quantities are directly proportional to each other if dividing one by the other gives a constant value. For example, if the masses and volumes of different samples of aluminum are measured, the masses and volumes will be directly proportional to each other. As the masses of the samples increase, their volumes increase at the same rate. As you can see from the data in Table 2-7 on page 55 of your text, or on the next slide. Doubling the mass doubles the volume. Halving the mass halves the volume. When two variables, x and y, are directly proportional to each other, the relationship can be expressed as y alpha x, which is read as y is proportional to x. The general equation for direct proportional relationships between the two variables can also be written as shown on page 55 of your text or on the screen now. The value of k is a constant called the proportionality constant. Written in this form, the equation expresses an important fact about direct proportion. The ratio between the variables remains constant. Note that using the mass and volume values in Table 2-7 on page 55 of your text or on the screen now gives a mass to volume ratio that is constant, neglecting measurement error. The equation can be rearranged in the following form. Y is equal to kx. The equation y is equal to kx may look familiar to you. It is the equation for a special case of a straight line. If two variables related in this way are graphed versus one another, a straight line or linear plot that passes through the origin at 0, 0 results. The data for aluminum in Table 2-7 are graphed in Figure 2-11 on page 55 of your text or on the screen now. The mass and volume of a pure substance are directly proportional to each other. We consider the mass to be y and the volume to be x. The constant ratio, k, for the two variables is density in this case. The slope of the line reflects the constant density, or mass to volume ratio of aluminum, which is 2.70 grams per cubic centimeter at 20 degrees Celsius. Notice also that the plotted line passes through the origin. All directly proportional relationships produce linear graphs that pass through the origin. Inverse proportions. Two quantities are inversely proportional to each other if their product is constant. An example of an inversely proportional relationship is that between speed of travel and the time required to cover a fixed distance. The greater the speed, the less time that is needed to go that certain fixed distance. Doubling the speed cuts the required time in half. Halving the speed doubles the required time. When two variables, x and y, are inversely proportional to each other, the relationship can be expressed as follows. Y alpha 1 divided by x, which is read as y is proportional to 1 divided by x. The general equation for an inversely proportional relationship between the two variables can be written in the following form. X multiplied by y is equal to k. In this equation, k is the proportionality constant. If x increases, y must decrease to keep the product constant. A graph of variables that is inversely proportional produces a curve called a hyperbola. Such a graph is illustrated in figure 2-12 on page 57 of your text or on the screen now. When the temperature of a gas is kept constant, the volume, V, of the gas sample decreases as the pressure, P, increases. Look at the data shown in table 2-8 on page 56 of your text or on the screen now. Note that pressure multiplied by volume gives a reasonably constant value. The graph of this data is shown in figure 2-12.
Two variables are directly proportional when their quotient is constant. In this example, when we divide the mass by the volume, we get a constant. From the graph, we see that when variables are directly proportional, when one increases, so does the other. Two quantities are inversely proportional when they have a constant product. In this example, when we multiply the volume and the pressure, we get a constant. From the graph, we see that when variables are inversely proportional, when one increases, the other decreases.
At this point, you should be able to distinguish between inversely and directly proportional relationships.